Our project is broken into 3 separate playbooks. First, let's configure the underlying AWS infrastructure to support our hybrid cloud deployment. The first playbook we'll review is named configure.aws.yaml, which builds our cloud infrastructure. Much like our test AWS comms playbook, we target the local control machine and include our vault. I've also included links to the documentation for both the official and community collections, which you can reference to better understand the options for each module. This playbook looks and feels a lot like Netbox. It's very long, but also easy to conceptually understand. First, we create a new virtual private cloud or VPC. This is a tenant environment inside AWS, which has a name, a region assignment, and a CIDR block. As a reminder, any subnets created within this VPC must be covered by the 10.0.0.0/16 block. Let's store the output from this operation in the VPC variable since we'll need to reference the VPC ID quite a lot. Next, we will create 3 subnets per our diagram. 1 for management, 1 for the IPsec VPN tunnel, and 1 for the cloud servers. We reference the VPC ID along with a specific availability zone, or AZ, within the specified region. We also include the subnet's name and CIDR in the proper places. The loop value is a list of dictionaries, each one specifying a different subnet, which is a technique we've seen many times before. AWS instances access the internet through an Internet Gateway, or IGW. Let's create one of those within our VPC, naming it IGW Globo and storing the result for use later. At some point, we'll need to reference this object to provide internet access to our environment. VPCs also have route tables, which are comparable to VRFs in traditional networking. We'll create a public route table that contains our management and VPN subnets. It's safe to manually index the subnets.results list because those results are provided in the same order that the subnets were created. This route table also has an IPv4 default route towards our just created IGW. We call this route table public because it has internet access. The private route table, by contrast, contains only the server subnet and does not route through the IGW. It's for internal use only, providing a secure location for our computing servers. As a quick note, I always recommend using intuitive names for these AWS objects, which makes troubleshooting easier when you inevitably make mistakes. I recommend doing the same thing when naming route maps, prefix lists, and access lists on network devices. At this point, we're finished with the VPC infrastructure and can focus on the computing infrastructure. We'll search for a specific Amazon image ID corresponding with the Palo Alto version desired. You can search for these images in the AWS console, and I selected a known good image for this demo. You can optionally specify a filter string instead of an image ID to programmatically search for images if you aren't sure which one to use. I opted to use 3 individual tasks rather than a loop because each security group requires a sizable amount of code. The management security group allows SSH and HTTPS, both of which are necessary to configure the Palo Alto. Also, you must provide a description to this module or else Ansible will raise an error. The rule list allows TCP ports 22 and 443 from any source, as you'd expect. The VPN security group allows IKE and IPsec traffic, enabling R1 to form an IPsec tunnel to the Palo Alto across the internet. This group permits UDP ports 500 and 4500. Note that UDP 4500 is used when IPsec encapsulating security payload or ESP traffic traverses a NAT device. The UDP header provides a port translatable shim for ESP, which explains why we must allow it inbound. Last, the server security group permits all traffic. We still must supply ports here, but since the protocol is all, those ports are ignored. The reason we have a wide open rule set is because we have a Palo Alto to enforce policy instead. There's no need to manage a giant AWS security group for server protection when you have a dedicated firewall, unless you wanted to apply intra-subnet security between EC2 instances. Some high-security environments may require this, but in our case, the presence of the firewall is sufficient. Next, we need to create the Elastic Network Interfaces, or ENIs, for the Palo Alto. We know there are three: one for management, one for VPN, and one for servers, which correspond to our three subnets. Every ENI gets a name, subnet association, IP address, and a list of security groups. The IP addresses are selected from the proper subnet, and each use the last octet of 77 for consistency. Each one is applied to the proper security groups as well, allowing the Palo Alto to communicate on the proper interfaces using the proper protocols. We'll store the result in a variable named ENIs_orig because we'll need to make some additional ENI changes after they've been created. The next task transforms this variable into a list of strings, extracting the interface ID from each result using the map filter. The results attribute is a list of dictionaries, but we want a list of string IDs instead. This is useful because having a list of interface IDs allows us to map elastic IPs to each interface more easily. That's exactly what happens in the next task. Ignoring the last interface for internal servers, we loop across the remaining management and VPN interfaces and allocate a new elastic IP or EIP for each. These are public IPs that are reachable over the internet. At this point, we've built all the core infrastructure needed to start deploying instances. We also have 3 ENIs that are correctly configured but currently unassigned. Let's deploy a new Palo Alto firewall as an EC2 instance. We specify our image ID again, along with the region, AZ, and instance details. I'm using an M5.large instance because the smaller instances only support 2 interfaces and our design requires at least 3. Thanks to our ENI result cleanup task, we can pass in the list of ENIs without any hassle. We'll create a single disk volume with a size of 60 gigabytes, which is the default for Palo Alto firewalls. We'll wait up to 120 seconds for the task to begin running, although the actual deployment takes much longer. Let's also specify the key pair, which I created in the first demo of this module, allowing SSH to access the firewall. Note that some products require a subscription, and currently Palo Alto is one of them. Be sure to read the terms and conditions before subscribing to this product because the Palo Alto can get very expensive if you aren't careful. Personally, I already subscribed to this product through the AWS Marketplace, which I didn't show in the videos. Once the firewall exists, we need to make one small modification to our non-management ENIs. That means we'll use a slice to skip the first element and loop over the remaining 2. AWS does not allow routed traffic to traverse EC2 instances by default, as it assumes all instances are end hosts. We need to disable the source destination check on these ENIs, and this can only be executed after an instance is deployed. That's why we couldn't do it when we created the ENIs. Our last step is to dynamically update our inventory with a new pan AWS group that contains a single host named pan-VM1. We identify the Ansible host as the management IP and the IPsec endpoint as the VPN IP, which are host-level variables associated to pan-VM1. We'll need both values later for follow-on configuration. These IPs are local variables which are printed out in the task name and represent the EIPs we've allocated for the firewall. When we review the output, you'll see the value of displaying these IPs, which can help with future troubleshooting and validation.